Hello, everyone. My name is Makoto Asai. I'm a project professor at the Keio University Global Research Institute, KGRI. In this movie, I will introduce my research project briefly. The title is Entropy-Driven Self-Assembly of Soft Matter. Okay, so let's start from this. What is the soft matter? Soft matter is a flexible material, as the name suggests. For example, there are many plastic products around us. They are soft matter. Also, our cell, proteins, and the DNA also soft matter, which makes us. So more concretely, the soft matter has a string-like structure like this that is made of several thousand of the carbons. This is also called polymer in the chemistry textbooks. Why is this kind of materials, which has string-like structure, called soft matter? As an antonym, there's a word, hard matter. This corresponds to the solid materials, such as metal and semiconductors. This materials is very, base materials for the modern, IoT technologies. So, in other words, what has a string structure as the backbone is soft. Roughly speaking, this corresponds to that the marbles are hard, while the yarn balls are soft. So then, why is the string soft? To tell the truth, this is caused by entropy. As you may know, the entropy is the indicator of the randomness. That is how complex to describe the situations we think about. Surprisingly, the nature is going toward the increasing the entropy, and the entropy flow is irreversible. This is off topics, but this truth is related to the why the time flow is one directions. This is very interesting. But okay, so anyway, the truth that the nature is going toward increasing entropy is called by second law of the thermodynamics. So here, let's imagine stretching a string like a stick, as shown in the light top figures. In this case, the way to describe the situation of this string is it's just one. That is, it's just a stick. And it's very simple, and this corresponds to that the entropy of this situation is very low. On the other hand, see the left bottom figure. In this case, the string forms a more complex conformation, and there are many ways to describe this situation. That is, the entropy of the situation is larger than the former situation. So in the nature, this situation is more reasonable than the former one. So imagine we stretch the rubber materials and stop stretching it, and the rubber will come back to the original form. We know well experimentally this truth, but this is caused by entropy. So this kind of interaction is called entropic interactions. And recently it has widely gathered attention from life scientists and related to the engineers. This is because the entropy interaction is very unique to the soft matter, which made a like living system, okay, in the nature. And there's a possibility for nature to use this kind of unique interactions, well, to build the living systems. But at this moment, we haven't known that entropic interaction enough, and it is an absolutely unknown science and the frontier of material science. The purpose of my research project is to develop the science of entropic interactions, leading to the key technologies to create autonomous and high efficient self-assembled materials like a living system. So my recent project focuses on the gel and the colloids as the base materials. This is very typical soft materials, typical and traditional soft materials. And we investigate new entropic interactions among these basic materials and aim for application to the metamaterials and the artificial life. So I think it's a time. So I finish my brief introduction here. So if you are interested in my research, please find more information on the KGRI website. Thank you for your attention.